Welcome, everyone. This is online Spintronics seminar number 107. The speaker today is Professor Peter Schiffer from Yale University. He'll talk about unusual magnetic phenomena in artificial spin ice. Peter is a professor of applied physics and physics at Yale. He received his PhD from Stanford, and he did a postdoctoral research appointment at AT&T Bell Labs. He has also held faculty appointments at Notre Dame, Penn State, and Illinois. And in addition to his faculty positions, he has also served in various university administrative roles, including the Vice Chancellor for Research at Illinois and Vice Provost for Research at Yale. He is currently serving as a senior fellow of the Association of American Universities and as a member of the Council and Board of the American Physical Society. His research focuses on frustrated magnetism, but has also covered a range of other topics, including colossal magnetoresistance materials, magnetic semiconductors, granular materials, and even superfluid helium-3. So with this, I'll hand it over to you, Peter. Please go ahead with your talk.
All right. Thanks, Carol and Shin, for inviting me, giving me the opportunity to speak. Is my voice coming through okay? Yeah. All right, great. So I'm going to talk today about artificial spin ice, and this is a topic that my group has been working on for more than 15 years now, and the long list of collaborators reflects that at different universities, as you can see. Especially want to call out my colleagues at Minnesota, Chris Layton and his group members who have provided samples, and Cristiano Nizzoli and the folks at Los Alamos who have done incredibly valuable theory work for us. So the outline of my talk, I'm going to give an introduction to artificial spin ice and explain what it is and why it's fun and interesting, why I've devoted 15 years of my research program to it. And then I'm going to talk about 3 topics of research in my group in the last few years. First, a new type of magnetic frustration called vertex frustration, and 3 different lattices that we studied that have this special type of frustration. Then I will talk about some magnetotransport results, and then finally noise from monopole plasma work that was done in collaboration with Scott Crooker at Los Alamos, and then I'll conclude and just give a quick survey of a bunch of other results that don't fit in any of these categories. So artificial spin ice really emerged from research that I had been doing since my postdoc on frustrated magnets. And geometrical magnetic frustration is a very current, very hot topic of research, and actually has been a topic of research for decades now. And it can be illustrated in its simplest form by 3 Ising-like spins on a triangle with anti-ferromagnetic interactions. If this one's pointing up, this one wants to point down. This one down here can't decide which way it wants to point, because according to this interaction, it wants to point down. According to this interaction, it wants to point up. It doesn't know what to do, and therefore it's frustrated. And it turns out that there are lots of materials in nature that have lattices based on triangles that are frustrated in this way and have unusual ground states and exciting different types of physics based on that frustration. One of these types of materials is a category called spin ice. And spin ice materials that were the proximate inspiration for artificial spin ice are pyrochlores, and they have big rare earth spins on a lattice of corner-sharing tetrahedra, like I've drawn here. And the rare earth spins are things like holmium or dysprosium, and because of the crystal field levels, the moments point either directly in or directly out of each tetrahedron. And the reason that they're called spin ice is that the low energy state in each tetrahedron has 2 moments pointing in and 2 moments pointing out. And that turns out to be exactly equivalent from a physics standpoint to the state of hydrogen atoms in frozen water, the stuff that if you're in a northern latitude is falling from the sky these days. The hydrogens in ice are 2 close to each oxygen and 2 further away. And this leads to very interesting statistical mechanics that is exactly mirrored in the spin ice. And that's why it's called spin ice. And this 2 in, 2 out structure is famous enough, it's called the ice rule. And both spin ice and real ice follow the ice rules. It turns out spin ice is very amenable to all sorts of experimental probes and has been the subject of many, many physics studies over the past roughly 25 years since it was first identified, including evidence for ground state entropy and magnetic monopole excitations and a number of other really interesting physics phenomena that come out of the ground state, highly degenerate disordered ground state in this frustrated system. So I studied real frustrated magnets for a long time, but the idea of artificial spin ice came up from the limitations of studying the real materials. And real materials, and any of you who are experimentalists who have worked with real materials will appreciate this, they can be tricky to work with. It's hard to change the lattice spacing. It's hard to change the geometry. You know, there are tricks that chemists and material scientists have, but it's hard to do. It's hard to control and identify defects locally, and it's hard to image individual spins. All of these can be done at some level, but they're challenging. And to study frustration in more detail, we wanted to look for an alternative path, which was to use nanometer scale lithography and microscopy to create an artificial analog to the frustration that you see in frustrated magnets and study what physics we could get out. And so the way we did that, and the field of artificial spin ice, a number of other groups are doing that, is by making what I put in quotes here, artificial spins out of lithographically patterning ferromagnetic films. So if you make islands out of ferromagnets with in-plane magnetization, and you put them close to each other, they will interact. And if you make them small enough, they'll be single domain, just like I've got drawn here, and they'll effectively act like big spins. And if you make them elongated, the moment will be along the long axis. And if you line them up like this, then they'll have a ferromagnetic interaction. If you put them next to each other like this, they'll have an anti-ferromagnetic interaction. And so this is a nice way to create a model system in which to study frustration. And just to show, these are some old data from a Notre Dame group, just to show in these with MFM data, if you make islands long and thin enough, you can see there's a black spot on one end here and a white spot on the other. That indicates the north and south pole of the magnet. You really do get things that behave like little single domain big spins. This is just for those of you who don't know how a magnetic force microscope works, this is just a little schematic of it that shows where you have a little magnet at the end of the tip, and you run it over your sample, and it gets pulled down with the north pole and pushed up with the south pole, which is how you can measure the magnetization of something like this. Now, there are other ways of imaging small islands. Another one that I'm going to be talking about is what's called XMCD PEAM, which is a synchrotron technique where you use X-rays, circularly polarized X-rays, to probe the magnetization of little magnetic nanostructures. The nice thing about this is that since you're shooting in X-rays rather than probing with a magnetic tip, you can probe the magnetic state of very delicate magnetic moments that might be flipped by an MFM tip. And you can also do it much faster than an MFM scan. And these are images of two little hexagons of magnetic islands like the ones I was showing you previously. And you can see on the time scale here, over a time scale of a few seconds, you can actually see the moments changing as a function of time, which is indicated by the little schematic down here. So you can probe very thin islands, thermally active islands, with this technique. Of course, you have to go to a synchrotron and compete for time in order to do it. So the simplest example of artificial spin ice is what we started with is something called square ice. And the geometry is given here. And you can see why it's called square ice. It's basically you put the elongated islands on the edges of a checkerboard pattern. And it can be analyzed most easily by looking at the vertices. So a vertex is sort of the points at which the islands converge. And so square ice has 4 island vertices. And 4 island vertices are analogous to the 4 moments on the tetrahedra of spin ice. And it turns out that a high energy vertex configuration would have all the moments pointing in, or in this case, all the moments pointing out. The lowest energy vertex configuration turns out has 2 moments pointing in and 2 moments pointing out, which you can see is going to be analogous to the spin ice materials. And this is a schematic just to give you a sense of the size and the energy scale. It's actually a picture from our very first paper back in 2006. So this is an MFM image of square ice where the black and white dots show the north and south poles of the islands. So you can see that you can very easily identify in this array which way the north and south poles are pointing. On the left here, I've given some of the physical parameters for making these systems. So the typical size is sort of a few hundred nanometers long, thickness of a few tens of nanometers thick, down to a few nanometers thick. Energy scales are typically hundreds to thousands of Kelvin. And we use electron beam lithography and liftoff for fabrication. And you can really map out what's happening in the collective state. And that's what's fun and exciting. One of the things that's fun and exciting about these systems is that you can really map out in detail the local configuration of the moments. And in this system, and actually in all the systems I'm going to be talking about, we used permalloy, just iron nickel alloy as our ferromagnet because it's very isotropic. So the shape anisotropy of the island determines which way the moments point. So in square ice, like I said, we can really understand it by looking at what happens at the vertices. And this will be a theme in much of what I'm going to talk about today. And it turns out if you have 4 islands at a vertex, you have 2 to the 4th possible configurations of the island moments. And they can be categorized in 4 types. Type 1, which is the lowest energy, has 2 in across from each other and 2 out across from each other. Type 2 also has 2 in and 2 out, but the 2 in that are next to each other and the 2 out are next to each other. That's slightly higher in energy. Type 3 has 3 in, 1 out, or 3 out and 1 in. And type 4 has all in or all out. And you can do something clever here, which Claudio Castelnuovo and Shivaji Sandhi and Roderick Missner came up with for real spin ice and was adopted for artificial spin ice very quickly, is you can start talking about the vertices as having effective magnetic charges. And so you might remember, those of you who recently took, or those of you who recently taught first year physics, you might remember that a dipole can be thought of as a bar with a charge on either end. You can think of these magnets, the little nanomagnets, as having charge on either end, in which case the vertex where they converge have a net charge. And so type 1 and type 2 with 2 in, 2 out have a net charge of Q equals 0. Type 3 has a net charge of plus or minus 2, and type 4 has a net charge of plus or minus 4. And so this turns out to be a very powerful way of thinking about the physics of these systems with these emergent charges that are not real charges, but they are effective magnetic charges, and you can understand a lot of the physics of these systems by understanding these charges. And I'll point out that these charges are effectively magnetic monopoles. Although if you talk to the particle physicists, you have to be very careful to explain that they're not real magnetic monopoles, because some of them get a little agitated if you don't explain that. So square ice turns out to be a bit of a boring system in its simplest form, in the sense that it has a well-ordered antiferromagnetic ground state of all type 1 vertices, which I've got highlighted here, 2 in and 2 out. You can tile the entire lattice with a type 1 vertices, and that turns out to be the ground state. And that's sort of nice from a simple model system standpoint, although it may be a little boring from a physics standpoint. It turns out it was actually quite difficult to get it into that collective ground state. It took the people working in the field several years to do it. There were 2 approaches that turned out to be effective in the end. One was to make the moments thermally active near room temperature, make them very thin, and then they would fluctuate back and forth, and eventually, as you cooled it down, they would settle in a ground state. The other is to take thicker moments, thicker islands that you can probe with an magnetic force microscope, and heat them up just above the Curie temperature of permalloy, and then cool it back down again. And then it turns out if you cool it down at a reasonably slow rate, as it goes through the blocking transition, they settle into a nice ordered state. And you can see here, compared to the first MFM image I showed, where the moments were disordered, you can see that you get beautiful ordering over quite a number of lattice spacings. And here is a domain wall to a different ordering. This ordering is, if you can think of it as an antiferromagnet, it's up, down, up, down. This one here is down, up, down, up. And of course, you have to have a domain wall between. Another example that people studied a lot is something called the Kagame ice, Kagame structure. And it's also called the honeycomb structure for obvious reasons. And this is a very famous model in statistical mechanics, a very, very famous lattice. And actually, there are a lot of materials with Kagame structure, 2-dimensional materials that people spend a lot of time studying. What's interesting about this system is that at each vertex, rather than having 4 islands meeting, you have 3 islands meeting. And what that means is that you have an effective charge, because there's an odd number of islands, you have an effective charge necessarily at every vertex. And if you've got 2 in and 1 out, you can call that a positive charge. 2 out and 1 in, call that a negative charge. And so you really have charges at every vertex in this system, which makes it a fun system to play with. It's quite different from square ice, where you can have uncharged vertices in the ground state. Here, the ground state necessarily has charges. And another way of thinking of that is that you have frustrations. It's like the triangle I showed in the very first slide. Now, it turns out because of that frustration, it's actually quite hard to get the moments to order in the Kagame lattice. It turns out that there is an ordered state. If you have long-range interactions, you do get an ordered state theoretically, but thermodynamically, no experimentalist has actually observed an ordered state yet in Kagame ice. There have been many, many people who have studied this. No one's ever gotten it to order thermodynamically. You can force it to order by using an MFM tip and various other ways, but no one has actually gotten it to settle into its long-range ordered state. But even though the moments don't order, it turns out that the charges can order. So even with a disordered magnetic state, you can have an ordered state for the charges. And this is one of the examples of how thinking about the charges rather than moments is powerful. You can get sort of a checkerboard pattern of the charges, where plus, minus, plus, minus, plus, minus. And it turns out that you can get that, and you can have, and you'll notice if you look carefully, the moments here are in a disordered state. I won't leave it up too long, but take my word for it, the moments are disordered here. But you can go to a different disordered state and still get charge order. And you can get actually the opposite charge order. You can just flip some of the moments, you'll get a different charge ordered state. So there's interesting physics here where you get emergent charge order, even though you've got a disordered spin state. And we did this thermal annealing trick on a Kagame ice, and you can see here, compared to the square ice, you can convince yourself pretty quickly that there's no simple long-range ordering in this image. There's a lot of randomness to it. So this is a large-scale MFM image where, again, the black and white spots correspond to the north and south poles. It turns out, though, even though there's no magnetic order here, there are little crystallites of charge order. So the red dots correspond to charge order of one sort, the blue dots correspond to domains of charge order of the other sort. So you get little crystallites emerging of charge order in this state, even though the spin order is completely lacking. It's really disordered from a spin configuration standpoint. Now, those are the two simplest lattices. It turns out that one of the real powers of artificial spin ice is that there are lots of different lattices, and I'm not going to give appropriate credit and just credit to all the different groups that have worked on artificial spin ice systems. This came from a review article that these folks wrote a couple years ago. Nice image showing a lot of the different lattices that people have made. And each one of these lattices, I'll talk about a few of them, but each one of these lattices turns out to have its own special physics, and people have made quasi-crystal lattices. They have made round islands that are circles, that are XY magnets rather than the Ising-like. So there's lots of different physics that can be explored here that I'll only talk about a small fraction of. So with that introduction now, let me go and talk about vertex frustrated lattices. So this is one of the unusual lattices that can be made. And this is a different type of frustration from what I talked about earlier. And it's what's been called vertex frustration by my theory collaborator, Cristiano Nizzoli. And this essentially comes about in certain lattices that have mixed coordination, meaning that they have vertices with 4 islands, vertices with 3 islands, and vertices with 2 islands. And what ends up happening is that you can't have each vertex in its local ground state. So in the Kagame and the square lattice, you could get all the vertices into their lowest energy states. It turns out in these 3 lattices that I'll talk about separately, you can't get all 3 lattices, you can't get all the different vertices into their individual ground states. And let me start by talking about the simplest one, which is something Cristiano called the Shakti ice lattice, which you'll see, and this is true of all these, this is just a square ice with certain islands missing. Basically, you pluck certain islands out of the lattice, leaving this mixed coordination of 4 island vertices, 3 island vertices, and 2 island vertices. And I've got the different possible states of the islands shown here, and you can see that you end up with the ground state of the 4 island vertex is type 1, like I showed before. The ground state of the 3 island vertex is very similar. Basically, we just got rid of one of the islands from the 4 island vertex. But the 2 island vertex is quite different. The ground state has the islands across from each other aligned, which is different from the ground state here, which means that this sort of tiling is incompatible with this sort of tiling. So you can't end up with the ground state for every vertex in the lattice. If you try to tile it with type 1, the equivalent of type 1 vertices from the square lattice, you're going to end up having excitations, shown by this little red circle here, on your 2 island vertices, or forcing those excitations onto the 4 island or 3 island vertices. And this is true of all the vertex frustrated lattices I'm going to talk about. Now, Cristiano has a way with words, and he called, just to separate the ground state vertices from the excited state vertices, he called the ground state vertices the happy vertices, and the excited state vertices, the unhappy vertices. And that language stuck, so that's the language I'm going to use. And it turns out that, like I said, you can't, in the vertex frustrated lattices, you can't get every vertex into the ground state. In other words, you're forced to have some unhappy vertices. And it turns out in Shakti, you have a fraction of the 3 island vertices. In fact, half of the 3 island vertices happy and half of them unhappy. And on each square plaquette, you're going to end up with 2 of the 3 island vertices. You have 4 3 island vertices on each square, so basically 1 on each side, and 2 of them, in this case, the bottom and the top, are happy, and 2, in this case, the ones on the sides are unhappy. So in each square, you have 2 happy and 2 unhappy, with a high degeneracy of possible states. And it turns out, if you have excitations above this ground state, it turns out, and I won't go through the details, that those are topologically protected. And so this is interesting. You can imagine interesting sort of loop topology for excitations in these states. It turns out there's other interesting physics here. The ground state is spin disordered. There's a high degeneracy of states that satisfy the 2 happy, 2 unhappy configuration. But even though the spins are disordered, you can get charge order again. And here again, the red and the blue dots correspond to charge ordering of either plus minus or minus plus minus plus. When we annealed the sample, we ended up with little crystallites of charge order, again, in this structure. And it turns out that not only you get charge ordering, you can even get charge screening when you have excitations, where the positive charges if you have an excitation above the ground state, the positive charges end up being surrounded by negative charges. So this is sort of a nice system to demonstrate the power of vertex frustration and this sort of thing. Even though the square ice has a nice well-ordered ground state, you remove some of the islands, you end up with a really interesting frustrated system with interesting topological characteristics. Another one is the Tetris ice. Tetris ice, it's called Tetris ice. I think you can probably see why we called it Tetris, because the little blocks here. Tetris ice, it turns out, if you look at it closely, it has a reduced dimensionality. It's got a reduced symmetry, and you can kind of break it down into stripes. The red ones here we called staircases for sort of obvious reasons. And the blue ones we call backbones, because they look just a little bit like the vertebrae of an animal. So it looks a little bit like a backbone there. And so it turns out that you can divide up this lattice into these 2 types of one-dimensional structures. And so even though it's a 2-dimensional lattice, it really breaks down into a lower dimensional system. And it turns out that in the ground state, the staircase, the frustration, the unhappy vertices live all on the staircases or next to the staircases, and the backbones are well ordered. And that's the ground state. So you do end up with the same idea that you're forced to have some vertices outside of their ground state. You can see this is that you've got the 2 moments aligned here along the top of the T. That's an excited state. Whereas here you have, in the backbones, you have all type 1 vertices going down. You have no frustration in the backbones, just in the staircases. And in this system, we imaged it with XMCD PEEM that I introduced earlier. And you'll notice that here we have much thinner islands, 3 nanometer islands. And you can see that we image it and you get a beautiful image out here. Ian Gilbert, who's now at Seagate, took these data. And you can see with the white islands are pointing in one direction relative to the X-ray beam axis. The black islands are pointing the other direction. You can see we can get a very nice image and map out which way the moments are pointing. And this is actually a state after going up to high temperature where they're fluctuating, going down to low temperature, and they settled into something very close to the ground state here. And one of the fun things about PEAM is that you can actually really, because you take images roughly once every 30 seconds, you can get a beautiful sense of the thermal fluctuation. So at low temperature, they're frozen. You go to high temperature, they're fluctuating faster than the imaging time. And so you can see that you can actually witness the thermal fluctuations. And because here things are moving faster than you can image. And you can actually make, and hopefully the movie will work, yeah, you can actually make a movie of these fluctuations. So this is just a bunch of images, actually. Andreas Scholl, who was helping us out at the ALS, took a bunch of images during warming. And you can see as it gets warmer and warmer, you can see the moments flipping back and forth and basically going from black to white to black to white. Those are the thermal fluctuations. And as it gets to higher and higher temperature, more of them are grayed out. And you can see now as we get to the highest temperatures, it's really all grayed out. So these are really thermal fluctuations in action where the moments are flipping back and forth, back and forth, back and forth. So you can actually see the thermal dynamics of the system. And we can map out, and you can see that these are basically the fraction of thermally active islands as a function of temperature from that same movie. And you can see that if you imagine going from low temperature to high temperature, the staircase islands become thermally active sooner because you've got the frustration there. So there's sort of more degrees of freedom, higher degeneracy. The backbones freeze out at a higher temperature. And so they go into a low temperature state where they end up being, they end up freezing out, they're more stable. And experimentally, one of the recent results we had, and this is work done by Hilal Saglam, who was a postdoc in our group, we did a bunch of samples with different lattice spacings. One of the fun things in artificial spin ice is that you can change the lattice spacing and change the strength of the interactions. And what we found is that going to smaller and smaller lattice spacings, you end up with ordering not just of the backbones, not just along the backbones, but actually across the backbones. And so again, these are ordered antiferromagnetically, and there are two ways of doing antiferromagnetic order, plus minus or minus plus minus plus. So that's indicated in the red and the blue. When there's a big separation between the islands, you get red patches and blue patches. When the islands are strongly interacting, the ordering is happening across all the different backbones. And it turns out that happens, you can show through the energetics and by calculating entropy, there's no energetic reason for this ordering to happen. It actually happens because of the entropy. So to maximize the entropy in the staircases, you end up getting ordering of the backbones. And so it's a nice example of a statistical mechanical phenomenon. This sort of thing has been seen in colloids and other soft matter systems, hasn't been seen in magnetic systems so much. Another system is Santa Fe ice, and this is similar to Shakti, a little bit more complex. I won't make you stare at it too long. It's a little bit messier, but the vertex frustration is the same. You end up with unhappy vertices on different islands, unhappy vertices on different places throughout the lattice, and you can't get rid of them. You're always going to have some fraction of unhappy vertices because of this combination of 2-island, 3-island, and 4-island vertices. And it turns out in the Santa Fe ice, and I won't spend a lot of time on this, but to just show you because it's sort of fun, you can draw lines through the unhappy vertices, and those lines intersect or originate in certain ones of these rectangular plaquettes. And it turns out that the ones where they originate are in the middle of certain sectors of the unit cells, these ones that I've colored in salmon here, and they originate there, and then they run through to the centers of other equivalent rectangles. And you can draw these lines through the unhappy vertices. They become effectively strings. And strings, as you know, are very interesting objects. They have interesting topological features. And so you can actually look at these strings as emergent properties, as an emergent excitation, collective excitation within the Santa Fe structure, where you not only have the unhappy vertices, but now you have the connected unhappy vertices being strings. Just showing you some data that we took. So this is a Xiaoyu Zhang, a recent PhD student, now a postdoc in my group, took these data, both MFM data and XMCD PEAM data. And the MFM data show that you end up, and this is as a function of lattice constant, you end up with the vertex fraction that you expect for the ground state. Basically, you go from having long strings to having short strings. As you reduce the number of excitations, you reduce the number of unhappy vertices. And that's simply because you're making it more strongly interacting with smaller lattice constants. But maybe more fun, with P measurements, you can do them at different temperatures, and you can actually look at the number of strings of a given length, and it turns out that that's activated. And so these strings really can be thought of as thermally activated objects, even though they are an object which is created out of the vertex states, which is created out of the moment state. So even though it very much is a collective phenomenon, if you just look at the length, the number of strings of a certain length, you end up with an activated behavior. And what Xiaoyu has been working on now is the motion of these strings. Turns out strings can wiggle and cross and connect and do all sorts of interesting things when they're dynamic. And we've got some results on that are working their way through the review process now. So for the next part of my talk, I'm going to talk about electrical transport through artificial spin ice. And this is basically, instead of having individual islands, we've got a connected network of little magnetic nanowires. And we attach leads to it and run a current through it and ask, what is the magnetoresistance? And a number of other people have worked on this as well, and turns out to be a fairly complicated problem. I'll show in a second. And the basic problem is that you end up with an ice-like state. So you have each little link in the network is a little nanomagnet, and because it's long and thin, it's single domain. And you end up with domain walls at the vertices of the nanomagnet, which is shown here. The white and black dots are each vertex with charge +1 or -1 in a Kagame structure. And what we did is simply measure the longitudinal and transverse resistance. Any of you who've done transport, this will look very, very familiar to you. We measure the voltage across as we run a current through, or the voltage along it, just to get a resistance out. And just to remind you, even in a simple ferromagnet, you expect interesting magnetoresistance, even in a continuous film. The so-called anisotropic magnetoresistance, or if you do transverse, it's called the planar Hall effect. And it's given by these expressions here. And again, this is probably familiar to most of you on this in this talk. It turns out that if you measure this array, you get all sorts of interesting, this is the longitudinal resistance, this is the transverse resistance. You get all sorts of interesting features in the magnetoresistance. This is just the resistance as a function of field, and you can see you get all sorts of bumps and wiggles. And I'll just point out that the transverse resistance, the features are at the 10% level, right? They're not small. And this is again in permalloy. So this is a permalloy structure. So it's not, it's not a subtle effect. And these angles here are different angles of the field relative to the current direction in plane field. And this has to be associated with the moments flipping. And these are just some sample data here. And you can see that as you sweep the field up, you get all these interesting features, and you sweep it back down again, and the features are very clean, very reproducible. And one of the fun things that really puzzled us is that there's an extreme sensitivity to angle. So this is the transverse resistance, and here I've got two different structures, one in the so-called armchair structure, one in the zigzag structure of a kagame. And you can see, look at the angles here, 0.2 degree difference in magnetic field angle. You get very different trajectories for the transverse resistance. And again, these are not small effects. And this angular dependence persists to zero field. So if you do these field sweeps and you just take whatever the resistance is at zero field, at the high field, well, if you do it at high field, you just get the planar, the sort of sine wave that you expect for the planar Hall effect. But if you go just at zero field and sort of take the zero field value of the transverse resistance, you actually get a noticeable angular dependence that has symmetry. See, it happens at 90 degrees very clearly here, and comes over again at I guess it's 135 degrees. It falls back down again. So there's very interesting things happen. And the fact that there's angular dependence at zero field implies that something's happening at the vertices, because in zero field, the moment has to align along the long axis of the wire links. And so something has to be happening in the vertices. And that makes it very interesting, because the vertices, of course, are where the charges are, where the magnetic charges are, if you think of the charges within the Kagame ice structure. And so how do you understand this? And if you try to do a simple ice model and networks of resistors, you fail, because you don't understand exactly what's happening in the vertices. So you really need, and you certainly don't get a transverse voltage from just, if you try to do sort of a Kirchhoff's law analysis, it ends up failing miserably. It's really hard, and you end up not getting the right results. And Kirchhoff's law wouldn't give you a transverse voltage in any case. So what you have to do is study the micromagnetics. And this idea actually came from Joe Chern, who's a theorist now at the University of Virginia. And what he suggested was using micromagnetics, and we use mu-max, to determine the magnetization map of the system as a function of field, and then assume a certain current, a uniform current distribution. You can calculate, based on this definition of the electric field from the anisotropic magnetoresistance, you can get what the electric field is based on a current, uniform current distribution, and distribution of the magnetization. And then once you know the electric field, you can integrate that to determine the voltage. And so I'll show you how that worked. So we took an SEM image, and we used that to get micromagnetics. And so this is just a color image that shows the direction of the magnetization in each part of the structure. And then we converted that to an electric field profile using this form here, assuming a uniform current going across. We took the magnetization and got the electric field at every point throughout the structure. And this is a blow up of that. So here's the magnetization. We get the magnetization, and each point from the magnetization, we can get what the electric field is at each point throughout the structure. And then what we do is we integrate the electric field to get the voltage. So you'll all remember first year physics, the voltage is E dot ds, integral of d dot ds. And so we just integrate the voltage going across to get the longitudinal resistance, and going across here to get the transverse resistance. And it turns out by simulating this way, so here are the experimental data, here are the simulation data. And you can see we don't get a perfect agreement, but we get pretty darn good agreement to understand what the resistance is. And this actually confirms, since we're doing an integral, we can figure out which part of the signal comes from the vertices and which part comes from the legs. And you can see most of it, in this case, comes from the vertices, not from the legs. So I'm just about out of time here. So I'm going to go quickly through this last little bit, and I'll be glad to answer any questions about it. This is studying the noise from the thermally active artificial spin ice. And this is really the work of Scott Crooker and Mateusz Gorisa at Los Alamos. And what they did is they did MOC, time-sensitive MOC, and they measured the fluctuations in the magnetization of artificial spin ice as a function of time. And you can see that they get fluctuations, and that associated with the moments flipping back and forth and back and forth. And it turns out that this is a really nice way of measuring the field-dependent behavior of artificial spin ice, because applying a magnetic field in MFM or an XMCD PEM is quite hard, but if you're doing a MOC measurement, it's quite easy. And so you're able to map out, and this is in square ice, you can map out what you would expect, which is in zero field, a nice ordered ground state, and a polarized state when you apply a strong field, either type 1 vertices or type 2 vertices. And this is the phase diagram you'd expect, and you can see that they get different noise in different parts of the phase diagram. And this is a noise map as a function of field. So in the Y direction, the X direction, you end up with no noise because there's a nice ordered state in zero field, no noise because there's a nice ordered state in high field. And then these stripes here correspond to the crossover. That's where you get a lot of noise. And these stripes at the very top and the very bottom are just an artifact because they measure the fluctuations only along the X direction. And I won't explain it. I have Scott and Mateusz are on the call. I apologize for not explaining in detail because it's a beautiful idea. It turns out the noise comes from monopoles hopping back and forth. And so you can really think of this as a monopole plasma, where there are plus and minus charges traveling around the structure, because there's sort of a crossover from this ordering to that ordering. And you can actually look at the noise spectrum and interesting things, and you can even get, you can actually, because it's in the audio range, you can even listen to the noise spectrum as you do a cut through the phase diagram. I won't make you listen to it, but it's kind of fun. You can also get noise from other structures, and Mateusz and Scott have done things on that also. And of course, there's much, much more. Other groups have explored all kinds of other physics. There are many other lattices and configurations that I didn't talk about, I showed earlier. People have done microwave studies with FMR of this. They've looked at the monopole dynamics. They've looked at monopole ordering. They've looked at various demonstrations of different spin models. There are quantum versions of this, three-dimensional versions, colloid versions, versions of superconducting vortices. People have studied devices, especially computing devices made out of this, and coupling to other physical phenomena. I'm at 50 minutes now. I can talk about a few more results from my group. Maybe I'm going to flash them up in about 2 minutes, but I won't discuss them at all. And then I'll end. We've looked at perpendicular anisotropy artificial spin ice, where the moments point out of the plane instead of in the plane. It turns out there's all kinds of fun things you can do there. Nick Bingham, a recent research associate in my group, demonstrated a 1D random field Ising model looking at avalanches with some theory support from Karen Dahman at Illinois and her group. Turns out you can get the 1D random field Ising model beautifully out of these systems by applying a field in a certain direction in square ice. And you can go beyond simple binary spins. If you put two spins close together, Joe Sklenar, who was a postdoc in my group, put two spins close to each other, turns out they act like quadrupoles, and you get anti-ferro quadrupolar ordering and ferro quadrupolar ordering, and all sorts of interesting physics from that. And Xiaoyu Zhang and Anthony Herman in my group are now looking at Y-shaped islands. Turns out these are tripoles. They've got 3 poles on the edges instead of 2, which is kind of fun, and we're working on that now. So with that, ran a little bit over, which I apologize. I'll be glad to go over and cover anything in more detail. Folks have questions, stuff I went through. Artificial spin ice is a lot of fun. It's really a playground for new physics. We've done a lot of things with it. There is a short review article that I wrote with Cristiano Nizzoli that I would recommend if any of you want to read more about it. And with that, I'll thank you for your attention.
Thank you very much, Peter, for this very interesting talk. Let's thank the speaker using the reactions buttons. So we're ready to take questions. If you have a question and you're in Zoom, please raise your hand. If you're in Twitch, you can just type the question and I'll read it for you. We'll start with Zoom. Other questions from the audience in Zoom? Shin, please go ahead.
Thank you, Peter, for the very interesting talk. I have one first clarification question. For the when you talk about the angle dependence of the magnetoresistance, and you specifically talk about when the field equal to 0, but I thought the angle is the angle between the field and the applied current. When H equal to 0, why would there still be an angle dependence?
Yeah, sorry. Yeah, that's I tried to explain that and apologize if I was going a little bit fast through it. So what we did is for each sweep, we took the value of the transverse resistance at a given field, and then plotted at a given field what it was. So, for example, the curve here at 500 Ørsted is the value at 500 Ørsted, and so the 0 field value is is the value that it had at 0 field, and then we did the sweeps at different angles.
I see.
I see. Does that make more sense?
Yes. So that's because different sweeping angles have different remnants state. Yeah, thank you. And
Sure.
One more question about the MR measurement, because when you do the imaging, you can see the fluctuation of the local spins. In the MR, even though you're measuring the whole thing, but do you observe those kind of local little fluctuations as a function time?
So we've started playing with that. So that's actually something that I want to look into. Jung-Sik Park and Brian Le, the 2 graduate students who worked on this, graduated, and so they didn't quite get to this, although Jung-Sik started, and there's a little bit of discussion in his thesis. We don't see it, but we didn't optimize the sample to look for thermal fluctuations. I think there will be very interesting physics if somebody makes the structures very thin so that it's more susceptible to thermal fluctuations. And one of the things that I'd like to look at, if someone else looks at it first, I'd be thrilled if they get to it first, would be to have a structure that one could probe near TC, near a ferromagnetic TC.
I see.
Because there necessarily have to be interesting fluctuations.
I see. Yeah. Thank you very much.
Sure.
Okay, thank you. Zishan Hu, please go ahead.
Okay, thank you. Thank you so much. A very nice talk. And I have a simple question. I don't work on this field. So at the beginning, you introduced the spin eyes from a historical viewpoint. So at the beginning, those are in the material that really focus on the spin. But later, I think nowadays because the nanotechnology, so you kind of scale up the size. Now you are working on the nano scale, not rather than the spin, like atomic scale. So, and also later you show some micromagnetic simulation to explain some of the data. So could I think in those, the nano scale, so those behavior can be described, so behave more in classical way, I would say.
Yes, that is exactly right. All the systems I'm talking about really should be thought of as classical systems, so they're not subject to quantum fluctuations. There is an important exception to that work, not that I didn't talk about, but that has been done by a group at D-Wave Technology, and my collaborator Cristiano Nizzoli worked on this. They have a quantum annealer at D-Wave, and so they're able to create effective Ising spins out of qubits and subject it to quantum fluctuations. And so they can model these systems. It's very impressive and somewhat complicated technology, but they can model these systems, these same structures with their qubit lattices and subject them to quantum fluctuations. And there was a very nice paper in Science on this, I think 2021, last year.
Okay, thanks so much. Yeah, thank you.
Sure.
Thank you. Let me also ask a question. So since the system is classical, you can do a Monte Carlo simulations, and I assume you would get an exact answer to any precision you want. So is there something in experiment that is not explained by simulations, or more generally for classical systems like that, what is the role of experiment versus simulations in understanding the physics?
Yeah, no, thank you. That is a question that that folks in the field get with some regularity. So, you know, there are two answers to that, and I'll give a very general philosophical answer, and then I'll give some specific cases. Philosophically, as an experimentalist, I always want to see what nature does instead of just thinking about it. So even if the Monte Carlo does give the same result at the end of the day, I'm happier if I see that nature behaves that way. As a practical matter, it turns out that, of course, real systems have imperfections and complications that the Monte Carlos don't have. So especially, and I'll give two cases. One is actually this nice drawing that we have in front of us here. We never would have expected this behavior just from simulations. I mean, guided by experiment, we ended up understanding the transport, at least to a reasonable level. I mean, if I go to the simulation results here, we get a reasonable facsimile of what the experiments gave. Here are the experiments, and here is the simulation. But we never would have tried that. We never would have gotten there if we had not done the experiments. Where I think there are more interesting effects is, if you look at interesting thermal effects, especially near TC with the annealing, it's complicated. Monte Carlo doesn't really work that well if your moments aren't simple classical moments. And if you're near TC, there are all sorts of spin wave fluctuations that happen in these islands. They're to low approximation, they are simple Ising spins to But in reality, of course, they're much more complicated. The tips bend and all sorts of fun things happen, especially as you go closer to TC.
Okay, thank you. There are a few questions in chat and in Twitch that I'm going to read for you. Is it true that thermal fluctuations shown for different stripes are almost at room temperatures?
Yes. So I think that's referring to the Tetris data, and so these data here. And yes, we can design these structures to make the islands very thin and the right size. And I have to give Laura Heiderman's group and Björgvin, whose last name I have trouble pronouncing, in Uppsala, Laura Heiderman's at PSI, credit for coming up with this sort of technology where it turns out that if you make the islands thin enough, they fluctuate thermally near room temperature. The energy scales are such that they are good single domain ferromagnets, and they are thermally unstable to flipping the moment back and forth. And so you really can be in a regime where the thermal fluctuation is just the moment flipping back and forth and back and forth. But in between the flips, they are good single domain ferromagnets.
So super paramagnetic, essentially.
Essentially super paramagnetic, exactly. So this is, I mean, one nice thing about this is that many of us have thought about super paramagnetism, but here we can actually see it, which is sort of fun.
Okay. Another question also in chat is other perspectives of using Spintronics for solving optimization problems, such as is done with the D-wave.
Yeah, so I'm not sure about optimization problem in particular. I guess people don't use exactly that language, but there is return point memory in these systems, and people have used this for reservoir computing, or at least attempts at reservoir computing. So there are interesting things one can do with these disordered states along those lines. Now, whether it turns out to be a practical next generation computing device, I'm not sure I'm ready to invest in a startup yet, but certainly conceptually it should work very well.
Okay, thank you. And I'm going to read the last question, but in the meantime, if anyone has more questions, please be sure to raise your hand or type it in chat, so we have time to ask it. So the last question for now is, what kind of codes do you use for simulations, and are they publicly available?
Yeah, so for micromagnetics, we use MuMax3, which is publicly available, and it requires a GPU, so it's quite fast when you get it on a GPU. My group buys for this purpose computers that I think are intended for gaming, and they work quite well. I don't know that you need to get a high-end gaming computer, but they actually look more interesting than most of the equipment in our lab. The Monte Carlo code, we don't write that in my group, although we've done some of it. So we don't have anything, but we don't have anything that's been put available on the web. But I think there are lots of people who have put Monte Carlo code up, made it available.
Yeah. let me just mention for people who may be interested in using micromagnetic simulations. So in the past, we've done tutorials on Mumax and the oomph codes. So you can go to our website and find the lectures there along with additional materials. So it looks like we are out of questions. So we're going to thank Peter again for a very interesting talk, but please don't go away. I'm going to stop the recording and streaming in a few seconds, and then everyone is welcome to stay and continue a more informal discussion.